Hey everyone and welcome. Today we're going to demystify something that's at the absolute heart of every electronics project: communication protocols. You can think of them as the different languages that all our little components use to talk to each other. And trust me, understanding these languages is the key to making anything work. So, let's get you fluent. So, picture this. You just got that cool new sensor you ordered. Maybe it's a gyroscope or a fancy light sensor. You're excited, ready to go, but then you hit that first big question. How do I actually get the data from this thing over to my main board, like my Arduino or my ESP32? Well, that's the exact puzzle we are going to solve today.
Okay, so at the most basic level, there are really only two ways data gets sent around. You've got the old school way, parallel, where you send a whole bunch of bits at once over a ton of wires. It's fast, yeah, but it's also bulky and kind of complex. And then you have the modern champ, serial communication. It sends data one single bit at a time. It uses way fewer wires, it's simpler to manage, and that efficiency is exactly why it's the standard for pretty much everything we do now.
Now, inside that world of serial communication, there are a few dominant languages, a few heavy hitters that you are absolutely going to run into. So we're going to focus on the big three that you'll see in nearly every single project out there.
And here they are, at a glance: UART, SPI, and I2C. You can see the trade-offs right away, can't you? UART is super simple with 2 pins, but it's also the slowest. SPI is an absolute speed demon, but it needs more wires to work its magic. And then there's I2C, the master of efficiency, letting you hook up a whole bunch of devices with just 2 wires. Let's break them down one by one.
First up, UART. The best way to think of this one is as a direct, private phone call between just 2 components. It's that simple. One wire is for transmitting, that's your TX pin, and the other is for receiving, the RX pin. It's reliable, it's straightforward, and it's perfect for things like connecting a GPS module or just sending debug messages from your board back to your computer.
And in the real world, using UART can be ridiculously simple. For instance, on an STM32 board, using its hardware abstraction layer, it's often just a single command. This one line of code here just tells the board which UART port to use, what to send, in this case the word hello, and bam, your message is off. It really is that straightforward a lot of the time.
Next up, we have SPI, and this protocol is all about one thing: speed. It works using what we call a master-slave architecture. The master, which is usually your main microcontroller, is the boss. It controls the entire conversation, deciding which slave device it wants to talk to and when. Now, that speed comes at the cost of using a few more wires. You've got a clock line, SCLK, which acts like a metronome, keeping everything perfectly in sync. Then you have 2 separate data lines: MOSI, which stands for master out, slave in, that's how the master talks to the slave, and MISO, master in, slave out, which is how the slave talks back. Finally, each slave gets its own chip select pin, so the master can say, "Hey you, it's your turn to talk." This setup allows you to send and receive data at the same time, which is why SPI is the king for things like SD cards and high-resolution displays. And that brings us to our third hero, I2C. I love to call this one the party line. Imagine a bunch of people on a single phone call. If you want to talk to one specific person, you have to say their name first, right? Well, I2C works exactly the same way. You can have a whole bunch of devices all connected on the same 2 wires, SDA for data and SCL for the clock. And this line of code shows that concept perfectly. To talk to a sensor, you use its unique address. In this ESP32 example, we're literally calling out to address 0x48 on the bus and saying, "Hey, give me 2 bytes of data." It's this addressing system that makes I2C so incredibly powerful for projects with a ton of different sensors, because you save a huge number of pins on your microcontroller. Okay, look, UART's SPI and I2C are going to cover probably 90% of all your projects. But what about that other 10%? What about when you need something a little more specialized, a little more robust? Let's look at a couple of protocols built for tougher situations. Meet CAN bus. This thing is an industrial powerhouse. It's literally the protocol that runs your entire car. It's designed from the ground up to be incredibly tough and reliable, especially in electrically noisy places like an engine bay. It uses a clever 2-wire system that's amazing at rejecting interference, and it has error detection built right in, which is absolutely critical for safety systems in cars and industrial robots. And what if you want to connect your project to the internet? Well, that's where Ethernet and Wi-Fi come into play. Ethernet gives you that rock-solid, high-speed, super reliable wired connection. It's perfect for something like an industrial IoT gateway that can't ever fail. Wi-Fi, on the other hand, gives you that amazing wireless flexibility for your smart home gadgets or remote sensors, but you do trade a little bit of reliability and use more power to get that convenience.
Okay, so that's a lot of options, right? How in the world do you choose the right one? And maybe even more importantly, what do you do when you've hooked everything up and it just doesn't work?
Think of this as your personal cheat sheet. It makes the choice pretty simple. If you just need a simple, short-distance link between two devices, UART is your friend. Need to blast a ton of data from an SD card as fast as humanly possible? That's a job for SPI. Got a dozen different sensors you need to hook up without using all your pins? I2C is the clear winner. It's all about matching the protocol to the job at hand.
Oh, but then comes that moment we have all experienced. You've wired everything up, you've triple-checked your code, you hit run, and you get nothing. Or just a stream of complete garbage. It is one of the most frustrating parts of working with electronics for sure.
This is when you bring out the secret weapon, a logic analyzer. This tool is basically magic. It's a device that listens in on those communication wires and shows you exactly what's being said, bit by agonizing bit. It lets you actually see the digital signals, which takes all of the guesswork out of debugging.
And I know, it might sound complicated, but it's really not. You just connect the ground and the signal pins you want to listen to. You tell the software a few basics, like what protocol you're looking for, then you hit capture. The software does all the hard work, decoding those raw ones and zeros into something you can actually read, showing you exactly where the conversation is going wrong.
And this is exactly why this tool is so essential. You're no longer just guessing, right? You're not thinking, is my wiring wrong? Did I get the speed wrong? No, you become a detective. You have the actual evidence right there on your screen, and you can just follow it to solve the problem.
So there you have it. You now have the foundation. You understand the languages that our electronics use to speak to each other, from simple two-wire chats all the way up to complex, super robust networks. You have a guide for choosing the right one, and you have the ultimate tool for figuring out what's wrong when things break. So the only question left is, what amazing conversation are you going to build?